You know, what's the real difference between a good programmer and a great one? It's not just about cranking out code, it's about a whole different way of thinking. Today, we're going to get inside that programmer's mind and unpack its most powerful secret, using the code that's already out there.
This quote just nails it, doesn't it? Programming isn't some solo act in a dark room. It's a craft that's been built up over decades by millions of people. The idea isn't to reinvent the wheel every single time, but to stand on the shoulders of giants, to learn from their work, and most importantly, to reuse it.
So, what exactly is this programmer's mind? Well, think of it like a mental toolkit. It's a set of problem-solving patterns that work no matter what language you're using, whether it's C#, Java, Python, JavaScript, it doesn't matter. This is about the universal language of how to think like a programmer. All right, so here's our game plan for building that mindset. We're going to start with the absolute basics, the foundation of linear data. Then we'll move on to more flexible structures like lists, see how algorithms make them useful, and then go beyond simple lines to things like trees and graphs. And we'll wrap it all up with the golden rule that changes everything. Every massive, complex piece of software you've ever used is built on some surprisingly simple foundations. And you know, the most basic way to organize data? It's just putting it in a straight line. So let's start there. And that brings us to the array. It's basically the bread and butter of programming, just a sequence of items stored one after the other. Sounds simple, right? Well, here's where it gets tricky. Different languages have their own little quirks. Does the first item start at position 0 or 1? These tiny differences can create a real Tower of Babel, which is why it's so important to see the core idea of the array, not just the syntax of one language. Okay, now check this out. This slide is so cool because it shows two completely different paths to the exact same result. On the left, we're using array brackets and an index to copy a string. Pretty standard stuff. But on the right, we're using pointers. We're talking directly to the memory addresses. It's a little more raw, a little closer to how the machine actually thinks, and it gives you this amazing glimpse under the hood. Arrays are fantastic, but they're also kind of rigid. You have to know how big they are ahead of time. So what happens when you need to add things or take things away without all that hassle? Well, you need something with a bit more flexibility. And that's where the linked list comes in. Instead of one big solid block of memory, it's a chain. It's built from these things called nodes. You can think of each node like a train car. It holds some data, the passengers, and it has a link, a coupler, that points to the next car in the train. This design is incredibly dynamic, and it's the foundation for so many other cool data structures. So, building on that idea, we get these specialized tools like stacks and queues. A stack is last in, first out, or LIFO. The analogy is perfect. Think of a stack of plates. The last one you put on is the first one you take off. A queue, on the other hand, is first in, first out, FIFO. And that's exactly like a checkout line at the store. First come, first served. And this brings us to the author's most passionate, most emphatic plea. I mean, it's in all caps for a reason. Reuse code. Seriously, the point is not to go out and build your own stack or queue from scratch. Why would you? They already exist in libraries that are optimized and have been tested by thousands of people. The real skill is knowing they exist and knowing when they're the right tool for the job. Okay, so we have all these clever ways to store our data, but that's only half the battle. Storing data is pretty useless if you can't actually do anything with it. And that's where algorithms come in. They're the recipes, the instructions that make our data come alive. Let's just take sorting. You've got bubble sort, which is super easy to understand. You just go through the list again and again, swapping pairs until everything's in the right place. Simple, but it is incredibly slow. Then you have quicksort. It's way more complex, using this clever divide and conquer strategy. But the payoff? It is ridiculously fast. This is a classic trade-off in programming, simplicity versus performance. Now, we mentioned quicksort is recursive. That word can sound kind of scary, but the concept is actually beautiful. All it means is a function that calls itself to solve a smaller version of the same problem. The analogy in the source material is just perfect. Imagine a door with a whole bunch of locks. To open the very top lock, you have to solve the problem of opening the one below it first. And to open that one, you have to solve the one below it. You just keep breaking the problem down until you hit the bottom, and then you work your way back up.
And see, once your data is sorted, you unlock some real superpowers, especially when it comes to searching. You could do a linear search, which is just the brute force way, check every single item until you find what you're looking for. It works, but it's slow. Or if your list is sorted, you can use a binary search. You jump to the middle, see if your target is higher or lower, and instantly throw away half the list. You repeat that, and it is unbelievably fast.
So far, pretty much everything's been in a nice, neat line. But the real world, it's messy, right? Data isn't always sequential. Sometimes it's hierarchical, like a family tree, or it's a huge, tangled web, like your friends on social media. To model that kind of world, we have to go beyond the line. This is where a tree structure is perfect, and you don't have to look far for an example. You use one every single day. Your computer's file system. You have a root drive, like your C drive. That's a node. Inside it are folders. Those are its child nodes. And those folders have more folders and files inside them. It's a perfect real-world hierarchy. And really, to talk about trees, we just need a few basic terms. It all starts at the top, at the root. Any node with things branching off it is a parent, and the things branching off are its children. A leaf is just a node at the very end of a branch with no children of its own. And the connections between them, we call those edges. That's it. With that vocabulary, you can describe almost any hierarchical system. So if a tree is a strict hierarchy with all these rules, a graph just says, forget all that. A graph is just a collection of nodes and the edges that connect them. That's it. No rules about parents or children. This makes it the most flexible, most powerful data structure we have. It's the engine behind Google Maps, your Facebook feed, even artificial intelligence. Understanding graphs is absolutely key to understanding the modern world. Wow. Okay, we have covered a ton of ground, from simple arrays all the way to these massive, complex graphs. But now, let's bring it all home and circle back to the single most important lesson in all of this. Here's the final takeaway, the thing I really want you to remember. The point of having a programmer's mind isn't so you can code a binary tree on a whiteboard from memory. It's about understanding the concepts. It's knowing what a tree is good for, or recognizing a problem that a queue can solve perfectly. Your real power, your true superpower as a developer, comes from finding, understanding, and creatively reusing the incredible solutions that other people have already built and perfected. That is how you solve bigger problems faster. So I'm going to leave you with this question to chew on. Think about a problem you're working on or just one you've been thinking about. But instead of asking yourself, how can I build this from scratch? I want you to ask, what brilliant piece of code already exists that I can use to solve this? That right there, that little shift in thinking, that's the heart of the programmer's mind.